Good morning. So starting this 27th lecture today, and as you know, we are discussing the MOS still today, but continuing our discussions on MOS devices. So in the last class, I was discussing about the CV plots of MOS capacitors, which look like this, and I can once again draw it because this is a very important thing. Let me discuss once again. If you consider this is C. C is the total capacitance of the MOS capacitor, and this is the V, which is the voltage applied between the gate. That V is equal to VG, but CV is very popular nomenclature. Therefore, I am just showing it as CV. C is the total capacitance of the MOS capacitor, and V is the voltage applied at the gate with respect to the substrate. This place of VG I am writing here because VG is a very standard nomenclature. As I told you that if you consider the equations which you derived in the class, where I have derived an expression for CD, the capacitance of the depletion layer, or you can call it a semiconductor surface induced capacitance. And also you know what is CI. CI is the insulated capacitance, all per unit area. Because these two capacitors are in series, the total capacitance C is given by the series combination of CI and CD, where CI is constant, dependent on the thickness of the dielectric film and naturally the material of the dielectric. In the case of oxide, that dielectric constant of oxide is roughly 4. Okay, permittivity is 4 into epsilon naught. And CD is a function of psi s, we have derived already. And again, psi s is related to VG, or the applied voltage. We know how psi s can be obtained from V. So therefore, I can plot CD for different values of applied voltage, and hence compute C, which is the series combination of CI and CD, for different values of the applied gate voltage. And that's how we get the ideal CV characteristics, which I told you looks like this. This curve is called the ideal CV plot, ideal CV plot, where the maximum value, the starting value is CI. This is your CI. Sometimes we call it COX, oxide capacitance per unit area. And this capacitance, the value of the total capacitance, when the applied voltage is 0, which assumes flat band condition, that is under flat band approximation. Remember, this capacitance I call it CFB, where CFB was defined as CI CDFB, already known to you, is equal to epsilon s divided by d by length, LD, divided by CI plus CDFB. That is this value. And you get a minimum somewhere here, and this point is more or less, this is what is called a threshold voltage of MOSFET. I write it V capital T. Okay. Now, this is an ideal curve obtained from theoretical derivations. Here, two things have been idealized. I have assumed that the flat band voltage is 0. That means the flat band approximation have been applied. And second is that the interface charge state, the effect of interface states has been ignored. So flat band condition has been flat band approximation has been applied while plotting this curve. That means we have assumed VFB is equal to 0. For this, VFB is equal to 0. And also the interface charge intensity, interface charge per unit area, that we shall discuss separately, is also 0. Under this condition, we get this ideal plot. This is known as ideal CB plot of a MOS capacitor. Okay? Then I told you that if you perform an experiment to measure this capacitance at a small AC voltage for different values of applied bias. So you can measure this C. This C, please remember, these C's are all differential capacitances. Dynamic. Over and above the DC bias, you are applying a small incremental voltage or a small AC voltage, then seeing how much charge, change in charge is taking place. That delta Q by delta V is that incremental capacitance. Okay, so that is how we have, this plot, please remember, is the plot of the incremental capacitance or AC capacitance versus voltage. Should be very clear in your mind. And that capacitance can now be measured by a setup something like this. It's a very simple setup, anybody can set it up in the lab. It is for spot measurements. However, sophisticated equipment is now, say in our laboratory, upstairs there is a HP profiler, where you can measure this, get the CV profile automatically. There is a ramp voltage generator inside. The ramp is applied across the device, and the capacitance is measured under small signal condition, digitally converted, and naturally there is a computer interface, and in the plotter or in the printer you can get some plot of C versus V. The standard things available now, and that can be done at different frequencies. As I told you, you can do that measurement at a higher frequency like 100 kilohertz or 1 megahertz, or you can also do that measurement at lower and lower frequency. The equipment which we have in our laboratory, standard HP equipment, cannot go that very low frequency measurement. It stops at 3 kilohertz. But for that very low frequency CV, or sometimes we call it quasi-static CV measurement, separate facilities available. It is a very difficult task. And I told you, if you take that high frequency measurement, we expect that there will be something like this. The curve is otherwise the same as the initial portion. So therefore I put another green line over it, and this measurement we call high frequency CV measurement, measured. High frequency normally define a frequency for which this frequency f is large compared to 1 by tau generation, recombination. In this case it will be generation. Thermal generation. Due to thermal effect, electron hole pairs are generated in the depletion layer under that positive bias applied at the gate, and that really produces the excess electrons in the inversion layer, in the surface. Okay, so this is the condition for which the high frequency measurement has to be taken. The frequency should be very, very large compared to the reciprocal of that generation time, lifetime of carrier generation. On the other hand, if you take the measurements at lower and lower frequencies, it is found the curve more or less remains the same, but there is a tendency like this. There is a tendency like this. And ultimately, the curve gets coincident with this curve. This is for different values of f, increasing f. These are called low frequency plots. These are called low frequency plots. Okay, as I mentioned in last class, that maybe this may be for say 500 hertz, this may be for say 30 hertz or 50 hertz, and this curve, which is coincident, practically coincident with ideal, that may be for say a frequency like 5 hertz or 1 hertz or 2 hertz at really very, very low frequency, for which, for this particular case, for a very low frequency plot, this I called very low frequency plot for which this frequency is very, very small, again, compared to tau generation. This is a very important thing. But let me tell you, the actual curves may not be exactly coincident with the ideal. I'll discuss it afterward shortly because I will not go into the details of the CV plot. But actual curve, let me tell you, will be slightly deviating even over 0 to VT region. This will not be exactly coincident with the ideal plots, rather there will be small shift. And that happens due to the interface charge, which you have not considered while plotting these curves. In fact, even this experimental plot, I have assumed that the interface state is not really causing much problem. That means I have assumed that interface state density is very small compared to the fixed oxide and other charges. Now, this derivation, which we did for your CV plot, for plotting the ideal case, ideal plot, ideal CV curve, was found to be rather little bit more complex than the simple derivation, because you had to integrate and there is a function of f and all these complicated things are there. But in a simpler way, I can derive the plot up to this, not beyond this point. So if you are interested, because this region of the characters is most important, let me tell you, for many applications. So for this particular region of variation, from at least from minus volt, minus V to up to Vt, a simpler derivation can be made. How? You remember, when a MOS capacitor, when you apply a positive voltage, a depletion layer is created. And what will be the expression for this depletion layer? I told you that it is equivalent to an N plus P diode. Only the barrier will be replaced by psi S. The barrier VBI plus VR or VBI minus VF will be replaced by psi S, which is the barrier potential at the surface with respect to the ground, with respect to the substrate. So in that case, naturally the expression for W, the depletion layer width, will be twice epsilon S, same old expression, only here I have to write epsilon S magnitude, the modulus, because this is square root and QNA. Please note that we are considering NMOS. In that case, the CD, the depletion layer capacitance just below the surface is naturally from our old expression is this. Okay? All right? Now, here you see that, and our total C is the series combination of CI and CD. So for different values of psi S, you can compute W, and hence you can compute CD, and hence you can compute C. There is no need of considering a more complicated equation which you derive. If you take the simple equation, you'll find they more or less agree. They're in detail, there will be some finite, that disagreement or slight error induced. But the ideal CV plot obtained from those equations are very, very, very more precise than the ideal CV plot which you can up to Vt. Because in this case, I am coming to this point. The beyond Vt, you cannot plot it using this simple equation. Now, what happened when V is equal to Vt? What happens? Qn, the inversion charge density, is just formed, isn't it? We have assumed that for V less than Vt, Qn is 0, but then this is just tends to form. That means I can say that just 0 but slightly more than 0. Or I can call it like this. Or Qn is very small. But thereafter, as I exceed Vt, as I apply a voltage V, which is more than Vt, then Qn definitely starts growing vigorously, exponentially. You remember that? The electron in inversion charge density grows vigorously. Now what goes to happen? What happens now? You see that this is your, once again let me plot this curve, this basic structure. This is a MOS capacitor. Here you are applying your V or VG, and this is ground. And this is substrate, and this is the oxide. Okay? And I said that when you apply a positive bias, a depletion layer is created. And that depletion layer is our W. Whatever I have, depletion layer width is W, whatever expression I have written here. Okay? As you exceed a voltage which is more than Vt, electrons start accumulating at the surface. This is inversion layer. And when your Vt is reasonably more than Vt, when your applied voltage is reasonably more than Vt, what happens is this electronic sheath which is formed is highly conducting. The effective number of electron here may be around 10 to the power 19 per centimeter cube or even more. So effectively what you are creating almost a metallic sheath, a thin metal film, as if like that, highly conducting film just below this oxide. So what it does, it tends to shield electrostatically the depletion layer. Because when you apply a voltage which is more than Vt, this highly conducting sheath, SHEATH, highly conducting sheath, this highly conducting sheath electrostatically shields the depletion layer from the applied bias at the gate. Same thing happens. That means most of the lines are terminated on this metallic sheath, and they cannot penetrate that to reach the depletion layer. So what will happen? Yeah, depletion layer width more or less becomes constant. It is not altered or affected when you apply a voltage more than Vt. So when this is very important, and so therefore W achieves a value which is roughly a value, I call it W max. And as a result, CD will achieve a value which is CD mean. And what is the value of that CD mean? Is epsilon S divided by W max. Same equation. And what will be the value of W max? It is a W value for which psi s is equal to twice phi f. Because at psi s is equal to twice phi f, the threshold has taken place. That is, we have crossed the threshold when psi s becomes or tends to cross the value of twice phi f. Therefore, you see that our CD mean is equal to epsilon s by W max, where W max is equal to the W when psi s is equal to twice phi f. That means it is equal to square root of twice epsilon s into twice phi f. I am always cautious to put the modulus sign. Why? Because it is square root. By chance it becomes negative, I am in trouble. So this is not possible physically. It cannot be an imaginary quantity. Therefore, it is better to put that modulus sign always.
So if I make such that the concentration of electrons is equal to the substrate.
Somehow that way, there are many ways of defining the threshold voltage. A dynamic definition is different. This is a static definition. We say that yeah, it is a point just, but then for strong inversion we add some quantity, maybe 2 Vt or 3 Vt or sometimes 6 Vt. Some little bit more voltage above Vt, a calculated from, I'll coming to the VT, I have not derived yet. So VT means the voltage at which psi s becomes twice phi f. But then instead of writing that, if you say that Vt is equal to voltage at which it is psi s equal to twice phi f plus an extra small voltage, about 6 times thermal voltage or 4 times, it depends. You know, many people have worked on it, some simple formula they have given. 6 Vt is a very standard thing. Then it gives, we say, the threshold voltage for strong inversion. We want threshold voltage, we call just threshold voltage. Other sometimes we call threshold voltage for strong. We'll be coming to that after. Okay? So this curve, this ideal CV plot, up to this point, forget about the Riemann region, can be obtained using that simple equation. And you don't have to go to any complicated thing, that's complicated formula. And you will get more or less, that for practical purpose, that these results are not that bad, okay? Now, what happens? Suppose I apply the gate bias here, not in a steady state fashion. Here what I am doing, I am applying 1 volt, 1.5 volt, 2 volt, 2.5. I am applying the voltage and waiting for a few seconds, then taking measurements. That few seconds is sufficient for, steady state to occur. But instead of that, suppose I apply a ramp voltage here, a linear sweep, and the sweeping rate can be changed, adjusted. And suppose I apply a very fast ramp here, or in fact I apply a pulse here. Pulse means infinitely fast ramp. And the voltage V is now more than Vt, maybe 3 Vt, but in the form of a pulse, or in the form of a very high speed ramp. High speed ramp. Then what is going to happen? This inversion layer formation takes some time. That is guided by this generation time, which I have already discussed. And this generation is not a very, very rapid process. So if you change the voltage rapidly, that is if dVdt is very large, then you are not allowing the inversion layer to form. If the inversion layer does not form, then will there be any shielding effect? If you do not allow the inversion layer to form, will there be any shielding effect? No. So in that case, this W expression, can it be limited by some twice phi f? We have seen that W becomes W max. As a result, CD becomes CD mean. Is it valid now? If we apply a voltage which changes rapidly, then what will happen? The depletion layer width will further, it is called deep depletion. This is what is known as deep depletion. Okay? So if you apply this voltage rapidly, that means if instead of steady state applying DC voltages in steps, we apply a voltage which varies rapidly, which increases rapidly with time, then this saturation effect will not take place. In fact, this capacitance will be falling and falling and falling. And ultimately, for large bias, if the breakdown does not occur, W tends to infinity, and as a result, CD tends to 0. And this portion of the curve, that means you will get, if you are applying a voltage here in the form of pulse or in rapid ramp form, you will get a characteristic the same from here to here, but thereafter it will go on decreasing. The capacitance neither will be saturated to a minimum value, nor will increase and then saturate to the maximum value of Ci. The case for high frequency and low frequency. Rather, the capacitance will continue to decrease. And this is what is known as deep depletion case. This happens when dVdt is very, very large. It's very, very large. This is very, very important. Okay? Can you tell me under which condition this kind of deep depletion takes place? Any one of you has any idea about it? Normal MOSFET applications, deep depletion does not take place. Take place in an indirect fashion. I'll be coming to that afterward when we discuss the MOS models in a different way. But normally, gate-induced deep depletion, that is called drain-induced depletion. Normally in the MOSFET, the terminology known as drain-induced deep depletion takes place. Whereas gate-induced deep depletion does not take place in normal MOSFET operation. But can you tell me when it is? It's CCD, charge coupled devices. Charge coupled devices is nothing but an array of MOS capacitors. Charge is transferred from one MOS capacitor to next, to next, to next. That's how we have a kind of delay line action. And that's how we can create a device called transversal filter. We can produce memories and other things, group memories and like this, recirculating memory. And there, the basic operation is based on the deep depletion principle. Okay. We now come to a simple derivation of the threshold voltage. Now, we have seen that the threshold voltage is a voltage. Let me come back to once again to VG, because that's how we are treating VG. CV plot, I have intentionally, it's called CV plot, that is why I have not written VT. So what is the definition of threshold voltage according to our simple way of visualization? Is equal to this when psi s is equal to twice phi f. And what is the expression for VG? It consists of two terms. One is the voltage across the insulator. The other is the surface potential. That is the expression for VT. I have already told you. The voltage, applied voltage, is divided into two parts. One, across the capacitor, the insulator capacitance, Ci. The other is across the depletion layer. So that depletion layer is psi s, and across the insulator it is Vi. And the whole thing I am writing for psi s is equal to twice phi f. And then what is the expression for Vi? Vi is equal to Qs. You remember I wrote it earlier. Qs divided by Ci from Gauss's theorem, plus again psi s, and everything for psi s is equal to twice phi f. And what is the expression for Qs? Qs consists of two parts, Qn and Qd. You remember, Qs is equal to Qn plus Qd. Qn is a charge per unit area in the inversion layer, and Qd is a charge per unit area in the depletion layer. Up to Vt, I have assumed Qn equal to 0. Okay, so Qs is equal to, therefore Qn is 0, and it is equal to simply Qd for V less than equal to Vt. For V less than equal to V or Vg less than equal to Vt, your Qs is equal to Qn, because we have assumed that Qn is practically not present. Okay? And then what is the expression for Qd? Qd is equal to Qna is the positive charge, negative charge density due to the unmasked ions in the depletion area per unit volume. And per unit area, you are considering per unit area. So what is the volume under that unit area? Only W. So this multiplied by W. And that W will be W max when psi s, I am considering psi s for this threshold voltage condition. So then what it becomes? It becomes 1 by Ci, and Qs is equal to Qd, and that is equal to Qna W max. So you substitute the expression for W max here. W max is equal to 2s, or rather I have written here, W max is equal to root over twice epsilon s twice phi divided by Na. So how much, what it becomes? Root over twice Qna epsilon s multiplied by twice phi f. That is your Qs by Ci. And then psi s, for psi s is equal to twice phi f, means only twice phi f. So this is the typical expression for threshold voltage under flat band approximation. So under flat band approximation, we have been able to derive an expression for threshold voltage, which is a very important parameter for MOSFET, which is given by this kind of equation. Let me once again write it here. Vt under flat band condition, so I am assuming VFB is equal to 0. Vt, assuming that flat band prevails, and that is given by 1 by Ci. Ci is equal to epsilon oxide, epsilon insulator divided by thickness di, and square root of twice Qna epsilon s twice phi f whole to the power half plus twice phi f. Please note that if it is NMOS, both the terms are positive, and if it is PMOS, both are negative. You can easily verify it. So there should not be any confusion. I am not writing that. But please note that for NMOS, threshold voltage under flat band condition is a positive quantity. It consists of two positive terms. This is positive as well as this is positive. And for PMOS, when the inversion layer consists of holes, both the terms are negative. So that the threshold voltage under flat band condition is a negative value. Please note Vt is positive and the terms are A plus B, both are positive. And for NMOS, and Vt is negative. Vt means under flat band condition. Please remember, this is for flat band condition. Vt ideal, sometimes we call it Vt ideal, is negative. Again, it consists of the two terms A and B, both are negative for PMOS. So this is a symbolic form of writing. This plus below the two numbers, it means that they are positive quantities, minus, they mean that they are negative quantities. There should not be any confusion. Sometimes we are confused with the signs. So don't consider the electronic charge and all this plus minus Q. You'll be unnecessarily in trouble. In solving problems, it is known that both the terms are positive numerically for NMOS and numerically negative for PMOS, and should be kept properly in mind. Now suppose you are interested in computing the inversion charge density, Qn. Then what is inversion charge density? As I told you that Qn is equal to Qs, the total surface charge density, minus Qd. and I am interested to compute the value of Qn. What has to be done? You note that our V, total gate voltage, is Qs by Ci plus psi s when Vg exceeds Vt, then this becomes, Vg becomes Qs by Ci. That means Qn plus Qd, I can write Qn by Ci plus Qd by Ci. Qs consists of two terms, Qn and Qd, plus I assume that psi s saturates to twice phi f. This is again a rather simplistic assumption. You remember that psi s increases rapidly but does not saturate. For simplicity, we assume that this saturates to twice phi f. Then you know the value of Vg. You know what is the Qd again, because phi s saturates to twice phi f. What will be the corresponding value of Qd? The corresponding, where you have to substitute psi s is equal to twice phi f there. Then it is an easy task to calculate Qn. Then you can easily find out from the same thing that Qn by Ci, Qn by Ci is equal to, what is this thing? This Qd by Ci plus twice phi f, what is it? Is a threshold voltage under idealist condition. So this is therefore simply equal to Vg minus Vt with Vfb is equal to 0. So it is an easy task to calculate the inversion charge density. You can calculate it, convert into a number, simply divide it by Q. If you divide it by Q, you get so many electrons per unit area stored in the inversion layer. Under this, therefore, I have made that approximation. One is regarding psi s as a function of Vg. I assume that with increasing Vg and then it saturates. This one is twice phi f. This is one approximation I have made. Again, based on the principle of the electrostatic screening, which I have introduced. And actually, remember, beyond this point, Qs increases with the surface potential following that e to the power Q psi s divided by 2 Vth rule. 2 Vth, we have discussed it earlier. But it is so rapid in the linear scale, for all practical purpose, I can assume it to be constant. And we have also assumed that Qn, and as a result D, the depletion layer width, W, as a function of Vg, again follows the same thing. This is of course at Vt. Similarly at Vt, this becomes W max. And I have assumed that Qn versus Vg curve is again something like this. This is Qn. Whereas the Qd component this is Qd. So these are the assumptions made in deriving those equations. Okay? This corresponds to W is equal to W max. That means psi s is equal to, all these three curves are related. Please clear for this. Origin is this curve. Psi s dependence on Vg. I am assuming it remains constant beyond Vt at twice phi p. As a result, W saturates to W max. Qn starts forming from Vt effectively, and Qd becomes constant or gets saturated beyond Vt. If I plot it in a semi-log graph paper, Qn versus V, Qn in the log scale and Vg in the linear scale, what will be the kind of curve? There you will really get the subthreshold behavior. Here you are actually finding that Qn becomes practically zero, but it will not be zero. It gradually goes into the subthreshold region. As a result, there is a current, and that current is called subthreshold current. And tendency today is to use devices in the subthreshold condition. Now, let us now introduce the concept of flat band voltage. We have assumed already is psi s is equal to 0 for Vg is equal to 0. But that is not true. So this is an idealized assumption. And this assumption was called flat band approximation. In practice, for Vg is equal to 0, psi s will not be 0. The amount of Vg needed to make psi s 0 is called flat band voltage. Therefore, flat band voltage is defined as the value of Vg for which psi s becomes 0. So this is an idealized assumption. This is the practical case, and therefore for a practical MOS diode, this is for a practical MOS diode, VFB is a voltage, gate voltage required to make the bands flat. Psi s is equal to 0 means flat band condition, required to achieve the flat band condition. Now why this thing happens? First let us consider the case of finite phi ms. Phi ms, that is the difference between the work functions of metal and semiconductor. Let us draw it. Suppose first let me draw the metal side. Vacuum level, and this is metal, and this difference is called the metal work function. Then there is an oxide. Similarly, there is a vacuum level for oxide, so I am not joining them. Same vacuum level, and then there is a conduction band edge and some valence band is somewhere. This is called the electron affinity of the insulator. Fermi level will be located somewhere near the band gap center, not exactly. And this is the oxide or the insulator. Whereas for the silicon semiconductor, we are considering P silicon in our example. Again, somewhere. So while drawing independently, I am assuming the vacuum level is a reference. So I have kept it constant. In practice, the Fermi level will be continuous. It will be something like this. And somewhere here, your conduction band, somewhere here, your valence band, and somewhere here your Fermi level. This I call the electron affinity of the semiconductor, and by analogy with the metal, I call it phi s. It's a semiconductor work function. Somewhere here, maybe they located our Fermi level of this oxide. It is very uncertain, let me tell you. And again, silicon dioxide is an amorphous material and cannot be strictly characterized by a band gap picture as indicated here. When you form this MOS capacitor, the Fermi level becomes continuous. Okay, and this is your metal side. So this is your semiconductor side. So this is metal, this is oxide, and this is semiconductor. So what is going to happen? What is going to happen? Now in this case, therefore, you know that your automatically the vacuum levels will be adjusted. This is now the vacuum level for the metal. This is phi m. Okay? In the semiconductor side, what will happen? Again, because it is p-type, situation will be like this. And somewhere here, your vacuum level. And the vacuum level will adjust itself something like this. You remember I discussed earlier in plotting the everything, heterojunction, metal semiconductor junction, everything. And this thing will be something like this. The EC and EV will be something like this. This is EC in the oxide, and this is EV in the oxide. And you see, therefore, you know that in this particular case, you note that phi m and phi s are not equal. Phi m is not equal to phi s. If phi m and phi s were equal, naturally energy band was flat up to the interface. So because phi m is not equal to phi s, the energy band will bend downward. And if you want to make the energy band flat here, what I have to do? I have to apply a bias here, a positive bias or negative bias. By applying negative bias, I am to, what has to be done? Positive bias or negative bias? Negative bias. Negative bias means raising this potential here with respect to this. So therefore, I need a voltage Vg, which is the voltage necessary to make, I am calling it flat band voltage, which is the voltage necessary for removing the difference. And that voltage should be simply equal to phi m minus phi s. A negative gate voltage, which is the difference between phi m and phi s, if you apply at the gate, the energy band becomes flat. This band will become flat up to the interface. Okay? You see that normally, let me tell you, you can note down for aluminum system, phi m is around 4.1 electron volt. This is for aluminum metal. For silicon, chi s is around 4.15 electron volt. Now, this is your, what is this? Your phi f. This is my definition of phi f. Q phi f or phi f, whatever you call it. So by doping, I adjust the position of EF with respect to the center of the band gap. Higher is the doping, EF will come closer and closer to EV, and in fact, finally it will enter into EV, and there may be a band gap narrowing, which I have already told you. So naturally, under usual condition, for the values of phi m and chi s, this is your electron affinity. The band will, for aluminum, silicon dioxide, silicon, p-type silicon system, the energy band is expected to bend downward. And to make it flat, I have to apply a little negative bias at the gate, which is the difference of the Fermi levels, difference of the work functions of the two materials, phi m minus phi s, to make it flat.